Hello, my name is Kendall Hendrix. I am a PhD student in the Department of Chemistry and Biochemistry, working with Dr. Peter Kroll. This is my work on the cross-linking of a commercially available HFC polymeric precursor. Hafnium carbide, shortened to HFC, is famous for having one of the highest melting points of any known solid. The exact values differ, but its melting point is in the ballpark of 4,000 Celsius, give or take a couple hundred. Due to its high melting point, HFC shows great potential as a material for high-temperature applications, such as spacecraft reentry and as a component in nuclear energy generators. Making hafnium carbide is usually a complex and involved process, using multiple precursor materials and techniques that require a relatively high degree of skill and effort. Folks have made HFC from a polymer before, but they had to create the polymer themselves. SHP-199 is a commercially available polymer for the production of HFC ceramics. It produces HFC without the aid of any other starting materials. Upon pyrolysis to 850 Celsius or above, the polymer turns into an HFC ceramic material, which is a simple and fast process. However, the resulting ceramic is very delicate. Here, I show a preliminary experiment that I conducted using a templated foam technique. I impregnated a piece of polyurethane foam with the SHP-199 polymer. At high temperatures, the polyurethane burns away, and the HFC ceramic is left behind in the same shape as the foam template. Any mechanical stress applied to the ceramic caused it to crumble. On the left, you see the foam as it came out of the furnace, and on the right, you see a piece of foam that has been transferred between a few containers and all of the fragments that have fallen off of the bulk. We propose that performing chemistry on the polymer before pyrolysis will result in a ceramic with improved mechanical properties. If we are to do any chemistry on this polymer, we need to understand its structure. We believe that the polymer was synthesized by the reaction of hafnium tetrachloride with 2-butyne 1,4-diol in the presence of water to create a dark brown polymer with the structure shown here. Carbon NMR supports the structure. Here we see an NMR spectrum for the plain polymer, which is the main spectrum, and the NMR spectrum of the butyne diol starting material in the corner. We see the same number of peaks in roughly the same position, one at 50 ppm and one at 83 ppm. Because the carbon is unchanged between the starting material and the final polymer, we would expect the carbon NMR spectra to resemble one another. We also determined the ratio of X monomers to Y monomers. To do this, we took a piece of pyrolyzed SHP-199 and performed a thermogravimetric analysis under air. Due to the mass loss we observed, we estimate that we have about 6 carbon atoms for every hafnium atom. Since monomer X has 8 carbons and monomer Y has 4 carbons, we can assume that our X to Y ratio is 1:1. With our structure established, we can now consider what chemistry we can perform. We chose 3 reactions to try. First is a nucleophilic substitution with an acyl chloride, which reacts with the OH groups in the polymer and releases hydrochloric acid. Second is a click reaction between a thiol and the triple bond in the polymer, which is catalyzed by light. Third is the hydrolysis of tetraethoxysilane, otherwise called TEOS, and subsequent dehydration reactions with the OH groups on the polymer. We tried the acyl chloride substitution with adipoyl chloride, which you may recognize as a precursor for nylon. Upon adding the adipoyl chloride to the polymer, a solid precipitate immediately began to form, and the entire mixture turned solid within about a minute. In the FTIR, we see the presence of the acyl chloride structural features serving as bridges between polymer strands. Next, we tried the click reaction by mixing our polymer with dithiothiol and leaving it in the sun as our light source. We see an alkane peak emerging at about 3,000 wave numbers from the carbon chain in the thiol. Most notably, though, if we look all the way down to about 900 wave numbers, we see a new peak that is indicative of an alkene double bond, which is what we would expect to appear if our click reaction with the alkyne was successful. We also performed the hydrolysis and dehydration with TEOS. A solid precipitate formed after a few minutes, and a nearly clear and colorless supernatant was left behind, which, compared to the initial dark brown color, is a great visual indicator of a successful reaction. Although we do see differences in the FTIR spectra, the thermal behavior of the polymer and the reacted product is of greater interest. The difference is clear. After reaction with TEOS, our material retains 20 percentage points more mass. Additionally, between 700 and 1300 Celsius, the TEOS product is remarkably thermally stable compared to the SHP-199 on its own. This is a great starting point, but we still have more to do. I would like to pyrolyze bulk amounts of each of these reacted polymers and evaluate the mechanical differences between them. Since the polymer arrives dissolved in water, the behavior of the polymer and other solvents is of interest as well. Ultimately, I would like to use the chemistry that I learned to make a porous HFC ceramic material. Thank you for your attention and have a wonderful day.